Okay, thank you, and welcome everybody to my talk. So I'm going to be talking about advancements in computer vision. Mostly, this is going to be a little bit of a deeper dive into some of the things that make computer vision models work. So a little bit of familiarity with the basics of AI models and computer vision is probably a little bit of a precursor, but it's okay. I'll try to explain my way through all the pieces that I'm going to be talking about here today. So generally speaking, I guess if I could get like a show of hands, how many people are familiar with computer vision as a discipline? Okay, great. Okay, so that's good. So the outline of the talk today is I'm going to start with basic computer vision and kind of go into the history of it a little bit, not too deeply. I'm going to be talking about, and this is just one example, but several models. But I'm going to start off with the YOLO model, which is the you only look once model. But at that point, I'm going to start spiraling into a little deeper, into more advanced models, like Detectron, for instance. At this point, any of these models familiar to anybody? Has anyone heard of these at all? Okay, great. Okay, so afterwards I'll be going into CLIP, which is a pretty popular multimodal model. And CLIP is kind of the foundation of everything else that has occurred in terms of advancements of computer vision and computer vision architecture. I'll be talking about multimodality. And finally, I'll be talking about video understanding models in brief. This is actually a very complex area, but video understanding is kind of the cutting edge right now of where AI computer vision is, and it warrants, in any talk about computer vision, it warrants at least visiting a little bit of how it works. So just, I know some people had mentioned that they're familiar with computer vision. Just to recap for anybody who's not, it's a field of AI that enables computers to interpret and process visual information from the world. So, for example, robot vision, the way that self-driving cars negotiate their environment, medical image analysis, augmented reality through the several meta glasses and other new augmented reality devices that are coming out are all incorporating computer vision models. So there's a lot of key areas and techniques that are part of the computer vision landscape. The most classical of those techniques was image classification, so determining what's in an image, labels in an image of different objects, object detection, so finding out where an object is located in some area of space, semantic segmentation, which means separating the space of an area or environment or an image into separate categories. For example, being able to determine that this is the room, you're all people in a room, and this is a TV monitor, and being able to provide meaning to those different pieces. And then more lately, image generation with generative AI and tools like Stable Diffusion. So some major challenges in computer vision include dealing with variations in lighting, occlusions, and viewpoint changes. And these have been classical issues with computer vision since time immemorial. And as computer vision models advanced, we surmount some of these changes and some of these difficulties through more complex neural network architectures. But they always remain, and they'll still be complex for quite a while. So there's a lot of scenarios where research is continuing. So this is not, in the grandest scheme, a solved problem. So, okay, so the beginning of computer vision actually goes back years and years, decades actually, into the 70s and 80s when people were started experimenting with robots and started experimenting with cameras and determining what they could obtain from images. Eventually, computer vision became its own discipline, and prior to 2006, people were using a lot of manual computer vision techniques or heuristic techniques to identify objects in an image. For instance, this visualization here is using an older technique called edge detection. And there's many kinds of edge detectors out there. Examples that I've listed here are the Sobel filters, Pruitt filters, and Canny edge detectors, which is one of the most popular techniques for edge detection. edge detection it's an area that I worked in a long time ago, and it can be a very challenging. It can be a very challenging technique to get right because images vary very widely from image to image on their edge data. Template matching is another one where if you take an object and you slide it over an image, you attempt to find copies of that object in the image or shapes in that image. That is another challenging aspect of image detection, where if you, for example, have a template, it can match certain, like say you were looking for a cat and you have the template of a cat, you can try to find you can find cats in an image, but let's say the cat rotates or there's some orientation change in the cat. That template no longer is so easy to use to match the cat in an image of cats all facing forward. So that's the basic idea behind the template matching. There's techniques that are used to determine motion in videos. For example, this Lucas-Kennedy method was a very popular technique to determine what's going to happen next using an underlying principle called optical flow, which I'll talk a little bit more in video understanding models. And then another classical technique is called histogram of gradients, which is used to locate change points in an image or gradients of intensity within an image, which can help determine boundaries and help do things like edge detection or look for objects. All of these techniques I'm just mentioning because there's quite a bunch of literature, a huge amount of literature in how to apply these techniques to computer vision, and it was all relevant prior to the 2000s. And so the 2010s rolls around, and an architecture called the convolutional neural network was used at that point to effectively make all those other techniques obsolete. And I'll go into that in a bit. So how many people are familiar with how convolutional neural networks work? Okay, and have heard about that. Okay, great, a few people. So the convolutional neural network is a sort of advanced, I call it a magical model, because what it can do, all those techniques that you saw beforehand that were used to that were handcrafted by engineers in determining edges, determining shapes in objects, finding out where things are located, it all became obsolete when this magical deep learning architecture became I guess, sufficient to use in production scenarios. The ConvNet was around for a long time, and it was used for digit recognition. I guess, developers of the ConvNet to the level that it had won Turing Awards and all that. But if you're all familiar with just the history of digit recognition. But but they became very popular, and I'll go into exactly at what point they become so powerful. But the idea is the convolutional neural network has several layers in it, and this is where a little bit of the knowledge of deep learning is important, but I'm not going to go too deep into it. Just note that it can take an image and break down the image into features automatically. It can find edges, blobs, other pieces of an object, like the zebra, for example, how long it is, the fact that it has a tail, the shape of its head, all those kinds of features. It can just extract that without having to think about it and create a specific filter for that. And you can use that for classification, zebra, horse, dog, etc. The convolutional neural networks are usually pre-trained with a lot of image data in advance. And again, I'll go into that, but they become really good at detecting objects once they are fed some database that they've been already that's already been labeled and optimized by humans initially to detect certain objects. So they can, not only are they good at breaking down features, but they can be advanced to do that in a much faster and much more efficient way. And there's lots of techniques which improve ConvNets over time. And they are the backbone of a lot of advanced object detection models. Some of them I've listed here. I'll go into a few more deeply, but there's also, just to mention currently, there's multiple different types of vision models out there, and another one you've probably heard of before if you're familiar with this space is the vision transformer. So that's the version of the transformer architecture that does a similar thing to the convolutional neural net. I just wanted to leave it at that because there are advantages and disadvantages to using either model, but if you look into this further, you'll see that both of these models are still very used. So why is deep learning vision so good? This is the point where it kind of all changed, right? So in 2012, again, if anyone has ever heard of the AlexNet challenge, or sorry, the ImageNet challenge and AlexNet, the ImageNet challenge was a yearly challenge that was used to determine if people would submit computer vision models and try to classify images with the competition, the goal to minimize the error rate of classification. So, for instance, who could get the best classification of a set of test images? And usually before 2012, models were reaching not super great accuracy in general, and they were using some of these older techniques which I talked about. But come 2012, I'll go into AlexNet in a bit. I just want to go into ImageNet a little. The ImageNet data set is a large database of images containing 14 million label images across 21,000 categories. It's humongous, and it was cleverly collected using Amazon. The initiative was started in Stanford University by Professor Fei-Fei Li and others who are involved in trying to solve this problem of image classification using computers. And again, the images that are the basis of ImageNet are like wide, everyday, single context images of many different things, from animals to objects you'd see in an office to scenes like rivers, forests, and whatnot. And so here's just the snapshot of some of the images in ImageNet. And again, just for more context, the ImageNet data set was used as a benchmark just to see how good the image detection models were at doing what they did. And so the ImageNet, because of AlexNet, the ImageNet challenge ended in 2017 because from that point on, computer vision models had become so good that they were essentially better than humans at detecting things. So this has been statistically determined that these models are I think these are 99% accurate now in many cases, where a human being at best is around 97 or 98% accurate for the best detection tests. So, but there are other challenges for image detection that continue, but this was just kind of set the space for that. So, let's go in just into what AlexNet is. Again, AlexNet is a convolutional neural network architecture. It was crafted by, if you've recognized the two figures below, on the left you have Ilya Sutskever, which you've probably heard if you're familiar at all in the AI space. He was at one point the lead scientist at OpenAI. AI scientist, and Geoffrey Hinton, who'd recently won the Nobel Prize for several advancements in machine learning, essentially bringing machine learning and AI to the state it is in today. So they had both been involved in the construction of AlexNet, as well as several other researchers. And the structure of this network is on the right. I'm not going to go too deep into it. I'd explain a little bit about how convolutional neural networks work layer-wise, but essentially what it's doing over these several layers is taking in images and breaking them down. And so in 2012, AlexNet won the ImageNet Large-Scale Visual Recognition Challenge with an error rate of 15.3%. So it was classifying about 85% of images correctly, which was humongous at that time. No architecture had approached that at even close to that at all. And so with that, it was off to the races with deep learning. At that point, deep learning had sort of become a household name because people had recognized that we have big data and we have other things that can make deep learning possible. Before, deep learning was not through neural networks because we didn't have things like Google Cloud. We didn't have huge compute engines collecting massive amounts of data. Now that we have the massive amounts of data, which deep learning relies on to make effective predictions, it just, at that point, the boom in AI actually, I believe, really started. And it's definitively with AI computer vision. And again, that's what I just mentioned, that deep learning techniques started becoming popular at that point. So So from that point on, that's kind of the basics. And I guess we'll start like maybe with the YOLO model, right? So what the YOLO model is a model that detects bounding boxes and detects images and puts bounding boxes around them. And for example, it can detect if somebody is moving in an environment. I'd showed an example before, just going back of the way the convolution right here, how people can be detected in an environment as they're walking. They're usually using some kind of model like YOLO to do this. So just wanted to highlight that a little bit. And the way that YOLO works is it basically is able to segment the region that it's looking at into different subregions through this idea of class probability maps. And it does that because, again, YOLO has a lot of training involved in it, but it's called YOLO because it's super, super quick in doing what it does. It doesn't need to understand a lot of the image or as much of the image as other models do in order to find the boundaries of an object in an image. And so that makes it good for things like camera, high-speed cameras, or cameras that are tracking things or looking at objects. It's used often for those. And the idea is that it's, again, called a single-pass network. I'm not going exactly too deep into why that is the case, but again, it's a probabilistic model, so it's doing things like detecting objects, regions of objects, and being like, okay, so there's something probably in these regions, and we can then narrow the regions down and be like, okay, these regions are most likely associated with this kind of object. Again, the idea is that it uses contextual clues about object classes, which it's pre-trained on, to determine whether an object is there. This is all in its like embedded space, its latent space. And again, right now we're on like YOLO version 10. The model continues to evolve and it continues to get more powerful techniques. So this video that I'm demonstrating here is basically, I coded up a simple sandbox for a lot of the demos that I've done here. And one of them is for the implementation of YOLO to do things like demonstrate the ability to detect objects in what's called an occluded artificial fog condition. So, for example, if this is, I've taken an image of a street, just somewhere out in wherever in the city, and I'm under some sort of artificial lighting, artificial fog. I've applied an increasing intensity of 0.6 to 0.9, and as you can see from left to right, if you can see, it might be a little hard to see, but on the bottom, the 0.6 fog, the YOLO model is able to detect a lot of different objects. But as you can see, as the fog increases all the way to the right, less and less detections are possible. And at 0.9, 90% fog occlusion, only a few things are detectable. But the nice thing about this model is that you can use denoising, and you can use things like dark channel priors. You can use several techniques to actually, even in like high fog conditions, be able to bring back the detection of YOLO up. And as the models have increased in power over time, even things like artificial fog become, or real fog or real occlusion conditions become less and less relevant, and the model becomes able to detect even more things. So that's just kind of like, I have these demos, by the way, at some point I will share. But from the model that I want to contrast that to is this model called Detectron. So how many people have heard of Detectron at all? Okay, not too many. Okay, so I just wanted to check because Detectron is actually one of the state-of-the-art models out there that are open source, developed by Meta for object detection and classification. And the Detectron model is actually a fairly complex family of models. So if you've heard the term foundational model, this kind of falls into that foundational-ish category of models for computer vision. Again, not too widely known because it's not like a consumer-facing thing, but if you are building an architecture for object detection and many other techniques, you'll use something like Detectron, potentially. So the idea of Detectron, it's more complex than YOLO. It has several other pieces to it, including models like a model architecture called the region proposal network in there, where it attempts to detect regions of an image and attempts to classify those regions in a more complex manner. And it's also got several other types of convolutional neural networks as part of it. So again, remember, as I mentioned, the ConvNet is kind of the backbone a lot of these architectures, and these architectures get more and more advanced based on that backbone. So here's an example of what Detectron can do. And this is, so again, I sent it up a sandbox to do this, but the ability, it can do many different things. So this is an example of background removal. With this, I took an image, just a random image I found on the internet of people, and I applied the RCNN module to extract the background, people from the background, and the training set of Detectron is based on a data set of it has human actors as part of it, so it can determine people. It has other objects as well as a part of it. If anyone has heard of something called COCO's, Common Object Context, that's, I talked about the ImageNet data set. There's several data sets out there that can be used for very specific tasks. So for things like detecting objects, a lot of different objects in an environment, ImageNet isn't as good as something like COCO's, because the ImageNet images are considered very clean, whereas the COCO's images are considered more complex because they have more variety, and therefore they're used for more complex detection tasks. There's other reasons too, but the background removal is advanced by this capability. So the idea is that the model masks out the things that it detects as people from things that it detects as background, and it can then remove that. And the idea is that, so as you can see, it's interesting because it detected everything as a person, including a thing that wasn't a person. It was more like the face of somebody on some mural in the background. But still, it was able to use its knowledge to kind of segment that out, which is kind of, it's interesting what you can get. It's kind of fascinating. Another thing that is pretty common, and that has been common in computer vision for a while, is key point detection. And so a version of the model, the Detectron model framework, uses something called key point RCNN, which it uses to kind of extract the key point skeletons of people. And those are, as you can see, these are kind of like stems of limbs and the entire body that kind of indicate the pose of a person. Now, why is this important? For several reasons, because there's lots of applications of pose estimation and generation these days, where a pose can be like, as you can see, this person in the bottom, their pose can be detected, and you can kind of, using actually generative techniques, you can actually generate the person in a different pose, which is actually part of, like, you know, how a lot of these like models out there that are creating like things like deepfakes and things are working, because they use pose estimation techniques to kind of like create a person doing something that they weren't doing prior. And so the Detectron model uses, like, again, uses common object context, COCO's, and COCO's provides extensive key point annotations. So if you want to do a key point system, there's other models to do this, like there's Open Key Point, a few other models, but you can do this through this one framework as well, because the data set, COCO data set, has a lot of that already trained. And then there's another example, not going too much into the details in the interest of time, but a common, another technique evolving from key point detection is instance segmentation. So now you can kind of highlight the entire person from an image. And this is interesting because instance segmentation and another subcategory of it called dense pose estimation allows you to actually create those avatars that you see in like the metaverse and applications like that. So it will take in an image and essentially replicate the person from that image or the segment of the outline of the person, and then can create like a virtualization of that person. So this is actually used again in like by a lot of different people who are developing these virtual experiences. But it's also used in traditional techniques of eliminating an background from images and finding people in like dense, collected, like again, foggy environments, other places where it's harder to detect because the camera hardware isn't sufficient. So, and then the final piece is panoptic segmentation, which is kind of like being able to detect everything from an environment. And it's called panoptic because it can literally look at the entire landscape and be able to label everything in a landscape. And so this falls under the category of what's called dense labeling, or any kind of labeling, object labeling, can take advantage of panoptic segmentation to separate these people from the environment. And let me show you. So now those are like image-based techniques, and in order to move to the next set of things, we have to talk about multimodality. So multimodality is interesting because who's heard of multimodal models at this point? I guess, okay, not too many people. That's good, and then I can explain it, and then people will be like, wow, okay. So multimodality it depends. It depends on understanding what the concept of a modality is. So a modality refers to anything that's like a specific kind of input. For example, image data is data is a modality. Pictures are a modality. Sound is a modality. Like as I speak here, you're hearing sound that's carrying information. That's itself a modality because it carries info. There's many other kinds of modalities out there. I'll go into that. Text is a modality. As you read text, text contains info. So all of these can be combined to enhance model performance. Just a little bit into the background of where multimodality came from, or where it was first applied, was to things like multimodal sensor fusion. So on the left, you have an image of an ultrasonic sensor, which is picking, if you've probably not heard of ultrasonic microdoppler, but you can think of it as like an ultrasonic radar. So as a person is walking through an environment, this ultrasonic radar can pick up the motions of their different limbs, like their torso, their hand motions, their footfalls, their head motions. These can all be picked up, and you can actually buy one of these sensors from there's ultrasonic microdoppler sensors out there for measuring the speed of cars and things like that, and other things moving in environment. The problem is with those sensors that they're low frequency. They lose high frequency data pretty fast. Then on the right, you have a seismic sensor. So a seismic sensor will pick up the motion of a person by the seismic vibrations that they make as they walk across some terrain. These vibrations, if you're familiar with seismology at all, are S wave, P wave, other kinds of seismic terminology for the different waves generated. But based on the shape of the waves, as you can see on the bottom, okay, I just have to make this a little bigger. Based on the shape of the waves, you can then determine some characteristics about the person. And so seismic sensors are good at certain things. Ultrasonic sensors are good at other things, but they both have their shortfalls. So what essentially you have to do is combine both of them via multimodal fusion, and then you get a combined, very intelligent estimate of what's happening. So this kind of stuff was done pre-machine learning. This again was done in the 2000s. I've done work in this area specifically before, but machine learning is where things have evolved, and so that's why. What I'm going to do is I'm going to play this video of something called the McGurk effect, and this will maybe highlight a little bit.
Watch this experiment. It's called the McGurk effect.
Ba, 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 ba.
What do you think he's saying? If you think he's saying da, 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 you are in the grand majority. But now, close your eyes and listen instead of watching.
Ba, 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 ba.
The voice is saying ba, ba, ba. Now, let's replay it without the sound. Yes, it's true. His lips are saying ga, ga, ga. So how is it that when the lips are saying ga, 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 and the sound says ba, 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 that our brains read da, da, da? The McGurk effect. It's an example of an auditory illusion. It's a great way to show that the accurate perception of information can involve the participation of more than one sensory system, in this case, vision with sound. We call it multimodal perception. The McGurk effect. It's a terrific example of the fact that the senses did not evolve in isolation from each other, but actually work together to help us perceive our world. When multiple senses are stimulated simultaneously, the brain begins to experience an information-rich learning experience and laps it up like ice cream. It encodes more information per unit time, and it remembers that information better too.
So the reason that I brought that up is because this is the foundation of why multimodal machine learning actually works and increases the fidelity of any kind of AI result or product or any kind of informational output, because our brains actually are advanced in a way to incorporate multiple modes of information to increase our understanding of the world. And so just like as a quantitative description of how this could work from a person's point of view is that, for example, if you have a sonic event and a visual event separated in a large period of time, for example, if you see a drum beating but hear no sound associated with it, and then 10 seconds later you hear a sound, you know those are two different events. If you see a drum beating and you see there's a small discrepancy of time of you hearing the sound of the drum, you can then assume your brain will see those as a single event. But then when there's a short interval of time between the drum beating, it's not super close, but it's short, between the drum beating and the visualization of the drum, then your brain actually is not sure. And you're not like consciously perceptive of this. Your brain is making an estimation to kind of fuse these into a single event. And that's where like your brain is doing that machine learning in order to understand that. So then that's where the intermediate discrepancies come into play. And again, multimodal models, machine learning works in the same way. So quickly, a quick description of unimodal architectures for learning. This is just a super quick review. So if you've heard of the transformer architecture, which I'm assuming everybody has at this point in some way, the transformer architecture is like the architecture everybody knows for doing machine learning on text data. It's the state of the art in natural language processing. I talked about vision transformers before, but this is specifically for text. And again, you can do text generation, natural language understanding on that single modality. For images, we just talked about the convolutional neural net. And for audio, you have an example. You can use something called a recurrent neural network to detect whether to get information from an audio sequence. And then you could and that's a single modality in itself, or any other kind of time sequence is a modality that an RNN can be used to do learning on. But the CNN can be also combined with an RNN and as you can see on the right, if you're not familiar with what's on the right, it's a spectrogram. It's a time frequency spectrogram of sound in the time and frequency dimension. It's essentially a visualization of sound, and that's machine learning through both a visual technique and an auditory technique can be used to understand what's going on in here. But again, those are unimodalities. So what happens is that when multiple modalities interact, they form cross-modal interactions, and they enabled enhanced decision-making in AI by allowing models to leverage complementary information. So what that means is, again, as I said, certain modalities have certain pieces of information, other modalities have other pieces of information. When you combine them together, they interact in the machine learning's embedded space, and they create a cross-modal interaction. And so that means that, like, for example, I'll give you an example in a second, but the things that can be done with understanding how cross-modal interactions work. Is anyone familiar with sentiment analysis here? Okay, right. So sentiment analysis is the understanding of how positive or negative text is, right, on its own. So you can actually do multimodal sentiment analysis. For example, if you see an image of a person sitting on a park bench, right? The person could be looking a certain way, pensive or whatnot. You don't know what they're thinking, but you could say the scene is positive. But then if you see text, or the person just got fired for the job and is trying to look their best in order to get through the day, then the sentiment of that decreases. So you can use a multimodal model to combine that information and have multimodal sentiment to understand truly what's going on in that visualization. You can ask. This is one of the most powerful techniques of multimodal understanding is visual question answering. So if you want to ask questions about an image, you can use a multimodal model to be like, what's going on in that image? What do you see over here? Again, the machine learning model can learn qualities that could not just be described through text about an image. How big is that object in the background, right? HCI, human computer interaction systems. So basically, people who are differently abled can use multimodal tools. For example, there's an application called Be My Eyes out there, which allows people with low vision to use this multimodal assistant to describe their environment, and it'll look at images and then audiate or speak as to what's in those images, because it can understand those images, and therefore the person can then hear. It's a great application, actually, so you could check it out if you get a chance. So I'm going to kind of wrap this up because there's quite a bit that I initially plan to talk about, but limited amount of time, but if I'm available later on if you want to ask some more details about this. So if anyone has, if we've talked about the CLIP model, I did a little bit. The CLIP model is a model which you can now build these things, that's why I'm pointing them out, is a model that does multimodal analysis on text and video, and text and images. And so you can see some of that assistant that you saw there is using models like CLIP in order to do this kind of stuff. So you could start to, again, build these on your own. If you take Python, Sandbox, and Colab, and you want to do multimodal applications, imagine making an application that you stack these kinds of learners on together, and then you can eventually get to a point where you're building something like Astra, where you actually can do multimodal learning, and that is basically towards the direction of general intelligence, right? Where a model knows things about the world. I mean, that's basically interacting with a person in a sense, if you kind of extrapolate larger. But these pieces are in place to do this kind of stuff now. And that's where the multimodal image advancements come into play. So what I'm going to do is I'm going to quickly go over a few more examples where multimodal learning is useful and powerful, just to limit that. So an example is in AI art generation. So if anybody's familiar with the image generators out there these days, they can do things like generate something in the style of Michelangelo, or generate something in the style of Da Vinci, etc. And that's what's happening in the background here. So I'm just asking the image generator to do this work. So essentially what happens is, this is a whole different area in its own, but neural style transfer is the category of things that is happening with this here. And the issue with this is that you can extract style from an image and apply it to another image, meaning you can take an artist's style with AI and you can style some other image with that, and there's ethical implications because the artist never gave you permission to do that, but it's very easy to do these days, and it affects contemporary artists, really. So this is a whole ethical area, but it is an advanced application of computer vision, started really in 2015. It started taking off. So that's pretty much, I'm going to kind of end this here because there's, again, a lot of advancements in computer vision, and yeah, there's tons of research out there. I will share references later, but yeah, that's where my talk is, and I think if anyone's interested in this stuff, you can reach out to me later about it. So.